Apache AVRO is a data serialization framework used primarily in big data systems for efficient, schema-based, cross-language communication. It supports compact binary encoding for smaller data sizes, with a focus on speed and schema evolution for interoperability. AVRO is widely used in ecosystems like Apache Hadoop and Apache Kafka for processing structured data. For more tech interview materials, please visit our website bowz8.com. Core components include 1. Schema. AVRO requires a schema defined in JSON to describe the data's structure. For example, a schema might define a record with fields like name, string, and age, integer. Schemas ensure consistency and play a critical role in both serialization and deserialization. 2. Serialization. Converts data into AVRO's binary format using the schema. For instance, name John, age 30 might be encoded as a highly compact binary sequence. 3. Deserialization. Requires the schema to interpret the binary data and convert it back into a readable format. The schema ensures correctness and alignment between producers and consumers. 4. Schema evolution. AVRO supports changes to the schema over time, such as adding or removing fields. This ensures backward and forward compatibility. Backward compatibility, new readers can understand old data. Forward compatibility, old readers can process new data. 5. AVRO containers. Container files, e.g., AVRO, combine data with its schema, making it self-descriptive and easy to share. These files also support metadata and compression. What happens under the hood? 1. Encoding. Data is stored in a compact binary format for efficiency. Default values can be specified in the schema for missing fields, ensuring smooth evolution. 2. Schema registry. Tools like Confluent Schema Registry integrate with AVRO and Kafka to manage schemas centrally, minimizing mismatches between producers and consumers. 3. Integration. AVRO works seamlessly with big data processing frameworks like Hadoop, for storage in HDFS, Kafka, for message serialization, and Spark, for distributed computations. Example use cases are big data pipelines. In Hadoop and Spark, AVRO is used to store data efficiently and process it quickly. Cross-language data exchange. AVRO allows systems written in different languages to communicate seamlessly by relying on its schema-driven approach. Streaming. In Kafka-based applications, AVRO is a preferred serialization format because of its compactness and schema management capabilities. Advantages include 1. Compact and fast. AVRO's binary encoding reduces data size and improves speed compared to JSON or XML. 2. Schema evolution. Ensures compatibility across versions, making it robust for evolving applications. 3. Multi-language support. AVRO supports Java, Python, C++, and more, enabling interoperability across diverse systems. 4. Integration. Designed to integrate seamlessly with tools in the Apache ecosystem. Limitations include 1. Not human-readable. Binary format complicates debugging without specialized tools. 2. Schema dependency. Both producer and consumer require access to the same schema for successful serialization/deserialization. 3. Learning curve. Requires understanding schema design and management. Thanks for watching. For more tech interview materials, please visit bowz8.com. Apache Beam is a unified programming model for defining and executing data processing pipelines across both batch and streaming data. Its unique write once, run anywhere approach allows you to develop pipelines that can run on different distributed processing backends, such as Apache Flink, Apache Spark, and Google Cloud Dataflow. Apache Beam is built around the concept of portability and abstraction, enabling developers to focus on pipeline logic without worrying about execution-specific details. For more tech interview materials, please visit our website bowz8.com. Core components include 1. Pipeline. The core abstraction in Beam where all data processing logic is defined. A pipeline includes steps such as reading data, transforming it, and writing results. 2. P-collection. The primary data representation in Beam, analogous to datasets. It represents a distributed collection of data that can be bounded, batch, or unbounded, streaming. 3. Transform. Operations applied to P-collections. Examples include Pardo, parallel processing, group by key, and combine. 4. I/O connectors. Beam offers connectors for various data sources and syncs, such as Google BigQuery, Apache Kafka, pub/sub, and relational databases. 5. Runner. Executes the pipeline on a chosen processing backend, such as Google Cloud Dataflow, Flink, or Spark. What happens under the hood? 1. Unified batch and streaming. Beam's programming model allows you to handle both batch, bounded, and streaming, unbounded, data seamlessly using the same abstractions. 2. Windowing. For streaming data, Beam divides unbounded data into logical windows, e.g., time-based windows, for processing. This ensures timely and efficient computation. 3. Triggers. Triggers determine when results for a specific window are emitted. Common trigger types include event time, processing time, or custom triggers. 4. Portable runners. Beam decouples the pipeline logic from execution, allowing pipelines to run on various backends without modification. Example use cases are ETL pipelines. Extract, transform, and load data at scale for analytics and reporting. Real-time analytics. Stream processing for applications like fraud detection and recommendation systems. Data integration. Combine data from multiple sources for unified analysis. IT data processing. Handle large-scale streaming data from IoT devices. Advantages include 1. Portability. Supports multiple runners, avoiding vendor lock-in. 2. Unified model. Simplifies development by supporting batch and streaming data in the same pipeline. 3. Rich SDKs. Provides SDKs for Java, Python, and Go, making it accessible for various developer communities. 4. Scalability. Leverages distributed systems for high throughput, low latency data processing. Limitations include 1. Complexity. The learning curve can be steep, especially for advanced features like triggers and windowing. 2. Execution overhead. Portability introduces overhead, potentially making it slower than specialized tools for certain use cases. 3. Dependency on runners. Performance is tied to the capabilities of the chosen execution engine. Thanks for watching. For more tech interview materials, please visit bowz8.com. Apache Drill is a distributed SQL query engine designed to query large-scale datasets efficiently across multiple data sources. It supports a variety of data formats, including structured, semi-structured, and unstructured data, without requiring data to be moved into a specific schema or storage format. This schema-free querying capability makes Drill ideal for exploring and analyzing diverse data in real time. For more tech interview materials, please visit our website bowz8.com. Core components include 1. Query parser and planner. Parses SQL queries and creates a logical execution plan optimized for distributed execution. 2. Execution engine. Executes queries in parallel across the cluster, leveraging Drill's distributed architecture. 3. Storage plugins. Connects Drill to various data sources like HDFS S3, NoSQL databases, e.g., MongoDB, Cassandra, and cloud storage. 4. Drillbit. The core service running on each node in a Drill cluster. Drillbits manage query execution, data processing, and communication between nodes. 5. Drill client interfaces. Allows users to interact with Drill through command line tools, REST APIs, or BI tools like Tableau. What happens under the hood? 1. Query submission. A SQL query is submitted via Drill's web UI, CLI, or BI tools. 2. Query parsing and optimization. Drill parses the query, determines the optimal query plan, and splits the task into parallelizable units. 3. Distributed execution. Drill bits process data in parallel, leveraging the cluster's computational power. 4. Data access. Drill accesses data directly from sources using storage plugins without requiring pre-processing. 5. Result aggregation. Results are combined and returned to the client application. Example use cases are ad hoc queries, quick exploration of datasets without predefined schemas, data integration, analyze data from diverse sources like HDFS, S3, and NoSQL databases, ETL processes, transform raw data into structured formats for further analysis, log and event analysis, query nested or semi-structured log data stored in formats like JSON and Parquet. Advantages include 1. Schema-free querying. Works directly with the raw data, making it flexible and fast for exploratory analysis. 2. Multi-source querying. Supports querying across heterogeneous data sources in a single query. 3. Scalability. Distributed architecture ensures high performance even with large datasets. 4. Rich SQL support. Supports ANSI SQL, including joins, subqueries, and window functions. Extensibility. Add custom storage plugins or functions to extend Drill's capabilities. Limitations include 1. High resource usage. Schema discovery and query optimization can be resource-intensive for large datasets. 2. Latency for complex queries. Performance can degrade for highly complex queries or large-scale joins. 3. Limited transaction support. Drill is not designed for transactional workloads or frequent data updates. Thanks for watching. For more tech interview materials, please visit AVRO.com. Apache Pig is a platform designed to analyze large datasets efficiently using Hadoop. Its high-level scripting language, Pig Latin, abstracts the complexity of Hadoop's MapReduce framework, making it a popular choice for ETL, extract, transform, load, workflows, and large-scale data analysis. It's used in batch processing environments and supports both structured and unstructured data types. For more tech interview materials, please visit our website AVRO.com. Core components include 1. Pig Latin, a simple scripting language that allows users to define data transformation operations. Pig Latin commands are compiled into MapReduce jobs. 2. Execution engine. Converts Pig Latin scripts into physical plans and executes them as MapReduce jobs on Hadoop clusters. 3. Grunt shell. An interactive command line interface where users can run Pig scripts interactively, debug them, and view results. 4. Modes of execution. Local mode. Runs scripts locally for small datasets. Hadoop mode. Runs on distributed Hadoop clusters for processing large datasets. 5. UDFs, user-defined functions. Allows users to write custom processing logic in Java, Python, or other languages to extend Pig's functionality. What happens under the hood? 1. Script writing. Users write a Pig Latin script defining their data processing logic. 2. Parsing. The script is parsed into a directed acyclic graph, DG, representing the logical operations. 3. Optimization. Pig optimizes the DG by combining operations or reordering them to reduce execution time. 4. Compilation. The logical plan is converted into a series of MapReduce jobs. 5. Execution. These jobs are executed on a Hadoop cluster with intermediate data stored in HDFS. Example use cases are ETL processes. Transform raw data into formats suitable for analytics and machine learning. Log analysis. Analyze server logs to detect trends or issues. Data aggregation. Perform summarization tasks like counts, averages, and totals across large datasets. Data preparation. Pre-process and clean datasets before passing them to ML pipelines or BI tools. Advantages include 1. Ease of use. Writing scripts in Pig Latin is simpler than writing native MapReduce code. 2. Extensibility. Users can write UDFs for custom transformations and logic. 3. Flexibility. Handles structured, semi-structured, and unstructured data formats. 4. Fault tolerance. Leverages Hadoop's fault tolerance features for reliable execution. Limitations include 1. Performance overhead. Higher abstraction can result in slower execution compared to optimized MapReduce or Spark. 2. Batch-oriented. Pig is not suited for real-time or streaming data applications. 3. Dependency on Hadoop. Requires a Hadoop environment to function. Thanks for watching. For more tech interview materials, please visit bowz8.com. Apache CouchDB is a document-oriented NoSQL database system. It is known for its simplicity, robust replication, and ability to scale horizontally across distributed systems. Data is stored in JSON format, making it versatile for applications requiring flexibility and offline capabilities. For more tech interview materials, please visit our website bowz8.com. Core components include 1. JSON documents. CouchDB stores data as individual JSON objects. Each document has a unique identifier, _ID, and metadata, including a revision identifier, _rev, for versioning. 2. CouchDB HTTP API. Provides a RESTful interface for all database operations like creating, reading, updating, and deleting documents. Accessible via standard HTTP methods, GET, POST, PUT, and DELETE. 3. MapReduce views. Enables querying of data using JavaScript functions. Data is indexed via MapReduce jobs, creating views that can be queried efficiently. 4. Replication. A built-in mechanism for synchronizing databases across multiple nodes. Supports unidirectional or bidirectional replication and can sync between servers and local instances, ideal for offline-first applications. 5. Clustering and sharding. CouchDB clusters distribute data across multiple nodes, ensuring high availability and scalability. Sharding divides datasets into chunks stored across nodes, enabling parallel processing. 6. Conflict resolution. Designed to handle distributed conflicts gracefully using deterministic algorithms. Keeps track of all document revisions, allowing developers to resolve conflicts manually if needed. What happens under the hood? 1. Storage. Uses append-only B-tree structures for storing JSON documents and their revisions. Append-only writes ensure durability and reduce fragmentation risks. 2. Data versioning. Every document update creates a new revision, identified by a _rev field. Revision tracking is integral for conflict resolution in distributed systems. 3. Replication mechanism. CouchDB replicates data between nodes using the _changes feed, which tracks document changes. Can replicate securely over HTTPS and works seamlessly with intermittent network connectivity. 4. Query execution. Queries rely on pre-computed MapReduce views for efficiency. Views are defined using JavaScript and are materialized incrementally as data changes. Example use cases are offline-first applications. Mobile apps that sync data with the cloud when reconnected, such as productivity tools or CRM systems. Distributed databases. Geographically distributed applications where data synchronization and conflict resolution are essential. IT systems. Storing and syncing device-generated data, including sensor logs. Content management systems, CMS. Systems requiring flexible schema and robust synchronization between editors and servers. Advantages include 1. Ease of use. HTTP-based API simplifies database interactions and debugging. 2. Offline capability. Robust replication makes it ideal for disconnected environments. 3. Fault tolerance. Built-in replication and clustering ensure high availability. 4. Flexible schema. No fixed schema, allowing storage of varied document structures. Limitations include 1. Performance constraints. Can lag behind other NoSQL systems for real-time analytics. 2. Query limitations. Limited support for ad hoc querying compared to relational databases. 3. Overhead in replication. Conflict resolution and replication metadata can add overhead. Thanks for watching. For more tech interview materials, please visit bowz8.com.